Picture this. Before the fiery inception of the universe we know today, before even the hot Big Bang, there existed a state known as cosmic inflation. It's a time when the universe expanded incessantly, with particles distancing at immeasurable speeds. Space and time as we understand them weren't fixed but evolved with the expansion and contraction of the universe. And this relentless inflation, it didn't just peter out over time. And the reason behind all this is, well, we'll dive into it later. During this cosmic inflation, something fascinating happened. Quantum fluctuations, brief and minute variations in the energy makeup of the universe, were stretched across the cosmic expanse, leaving indelible imprints on the fabric of space and time. As these fluctuations got older and more stretched, they would appear on larger scales while the younger, less stretched ones would present themselves on smaller scales. Yet over time, these fluctuations would become unobservable as they get stretched beyond our cosmic horizons. Now here's where it gets interesting. Cosmic inflation didn't last forever. In certain pockets of the universe, this rapid inflation came to an end, and the energy transformed, marking the beginning of the hot Big Bang state, a phase referred to as cosmic reheating. These energy fluctuations during inflation morphed into density fluctuations, setting the stage for the large-scale structure of the universe as we observe it today. And here's a final thought to ponder on. It's believed that there are vast regions still undergoing cosmic inflation. For every spot where inflation ceases, a new one is born as the inflating regions continue to grow. It's a never-ending cycle that suggests an intriguing possibility that cosmic inflation may be eternal. But the mystery behind it all is, that's the story for another part of our discussion. Hey there, Curiosity Explorers! Ready for another dive into the unknown? I'm joined today by our incredible commentator, Sonia.
Hey, adventurers! Always remember, the world is full of mysteries waiting to be unraveled. Let's explore some of them together.
And we're set to do just that on this journey with you. Each day, we're unpacking something new and intriguing in the world of science, history, and beyond. So if you haven't done so already, please subscribe to the Curiosity Wonderland. Leave your comments and don't forget to share it with your fellow Curiosity Explorers. Your participation helps us keep this adventure going. Let's dive in, shall we? Let's delve deeper into the concept of cosmic inflation. As we were discussing, our universe is teeming with matter and radiation that we can observe. Over billions of years, all this matter has clumped together due to gravity, forming this beautiful cosmic web we see today on a grand scale. There are clusters of galaxies, individual galaxies, clouds of gas, stars, planets, and more on smaller scales. And throughout all of this, the universe has been expanding and cooling. This process of expansion and cooling has been going on since the very early moments of the hot Big Bang. But it's critical to understand that the Big Bang wasn't the absolute beginning of the universe. Preceding it was a period known as cosmic inflation, which set up the conditions for the hot Big Bang we usually refer to as the birth of the universe. Now, this notion of cosmic inflation paints an entirely different picture of the universe. It can be quite challenging to intuit living in an expanding, cooling universe, and it becomes even more complex when we talk about cosmic inflation. Before Einstein, we used to think of space and time as fixed and absolute. But now we understand that's not the case. Think of it this way. Imagine a particle existing somewhere in the fabric of space-time with another particle a short distance away. The only thing influencing them is the expansion of the universe. How would this particle move relative to you? If our universe were filled with radiation, it would expand with time. The distance between you and this particle would increase proportional to the square root of time. If the universe were filled with matter, it would expand with time raised to the power of 2/3. But during inflation, space expands exponentially. Unlike a radiation-filled or matter-filled universe, which dilutes as it expands, an inflating universe doesn't slow down. The expansion is relentless. It's driven by the energy inherent to space itself, and the rate of expansion remains constant over time.
So that's how the universe expands. But how does this relentless expansion impact the particles? If I'm understanding correctly, wouldn't they keep moving away from each other?
Exactly. The particles would appear to recede from each other due to the expansion of the universe. But remember, this is an oversimplification of the reality. Things like space-time curvature and the presence of matter and energy do have an effect. Regardless, it's an interesting way to think about the expansion of the universe and its effect on matter.
That's fascinating. But what about after inflation? How does this set up the conditions for the hot Big Bang?
That's a great question, but we'll get to that in just a moment. So let's delve deeper into this concept of the expansion of the universe. After a certain amount of time, the particle we were talking about earlier would double its distance from you. Now, during inflation, this expansion is not just exponential, it's also rapid. That doubling would only take about 10 to the power of -35 seconds. But the real defining trait of inflation isn't its speed, it's the relentlessness of the expansion. In fact, after the same period, the particle would be 4 times its initial distance from you, and after 3 times 10 to the power of -35 seconds, it would be 8 times its initial distance. This trend would continue for as long as we want to measure. If we were to keep going, after 10 to the power of -34 seconds, that particle would be 1,024 times as far away from you as it initially was. After 10 to the power of -33 seconds, it would be 1 followed by 30 zeros times its initial distance. And after just 10 to the power of -30 seconds of inflation, the nearby particle would be about 1 followed by 300,000 zeros times as distant as it was initially. So if our universe began full of these particles, they would quickly be driven away from each other to the point where no two would ever see each other again. Now let's consider the condition of space itself at the beginning. It may have had an interesting intrinsic curvature to it. It could have been knotted, twisted, turned, or even spherical. It could have been full of topological defects, with holes throughout it.
The more we talk about this, the more I realize how complex and fascinating our universe is. But I'm also curious to know, what does this mean for us? For life as we know it, or for our understanding of the universe?
That's a brilliant question. The effects of inflation are far-reaching and incredible. But to truly understand that, we need to delve even deeper into the fabric of the universe. Let's continue on our journey of discovery and see where it takes us. Let's continue. Inflation causes space to expand exponentially, which quickly results in any pre-existing curved or non-smooth space appearing flat. And this is due to there being a large amount of energy that is intrinsic to space itself. As the fabric of the universe expands, new space gets created, also with that same amount of energy inherent to it. This is why the expansion is relentless. Interestingly, I just attended a lecture recently where the speaker used a fantastic analogy to describe this. Imagine a crumpled piece of paper. If you were an ant crawling on it, you would perceive it as being full of hills and valleys. But now if you inflate this piece of paper like blowing up a balloon, our ant would now see the surface as nearly flat. That's similar to how during inflation, any initial geometry of the universe gets stretched to such a large scale that any region we look at appears flat.
What a coincidence. I've recently watched a documentary that used a similar analogy. It was about how quantum fluctuations work. These fluctuations happen on very low energy scales and on timescales that are extremely short compared to anything we observe. In our universe today, they act like virtual particle-antiparticle pairs, popping in and out of existence. They don't result in anything interesting happening. They simply add a small amount of extra energy to the fabric of space itself.
That's right. This zero-point energy of empty space is what we equate to the dark energy we observe now. But in the early universe during inflation, the expansion rate was much, much greater than it is today. Trillions upon trillions upon trillions of times greater, in fact. Which brings us to the next point. So let's keep exploring. So let's unpack this a bit more. The energy of the quantum fluctuations during inflation was much larger than it is today. They were about 100 orders of magnitude larger, in fact.
That's quite a significant difference. It's mind-boggling to think about.
It really is. The energy inherent to space jumps up and down by about 0.03% randomly due to these quantum fluctuations. However, during inflation, these fluctuations didn't remain localized but were stretched across the universe.
So these fluctuations from the past are still present today, but in a stretched form.
Exactly. And what's more, the value of energy inherent to space varies from place to place, with older, more stretched fluctuations appearing on larger scales, and the younger, less stretched ones appearing on smaller scales.
It's like a cosmic tapestry woven over time.
That's a good way to put it. The smaller fluctuations get superimposed atop the larger, older ones. These fluctuations cause density variations in the early universe, which in turn lead to the temperature fluctuations we see in the cosmic microwave background.
So the imprinted patterns we see in the cosmic microwave background are essentially echoes of these early quantum fluctuations?
Precisely. And with every tiny fraction of a second that passes during inflation, the smallest subatomic scale we know of today, known as the Planck scale, gets stretched to the size of our currently observable universe and beyond. This relentless expansion of the universe meant whatever occurred a tiny fraction of a second ago is now more than an entire visible universe away. On all scales, there should be these quantum fluctuations that are not only imprinted but are also continuously newly imprinting themselves on the universe.
So in essence, we're seeing a snapshot of the very earliest moments of the universe every time we look out at the cosmic microwave background.
Precisely. It's a glimpse back to the dawn of everything we know today. Fascinating, isn't it? Moving forward, let's consider this. Inflation doesn't last forever everywhere in the universe. There's a small but finite probability that with every new space created, inflation will be brought closer to its inevitable end.
So it's like a cosmic countdown.
You could say that. One way to visualize it is to picture a ball that rolls very slowly atop a flat plateau. Below the plateau is a valley. If the ball rolls into the valley, inflation ends. This random distribution of probabilities applies each time new space is created. And when the ball does reach the edge and rolls into the valley, inflation ends and the energy transforms into the energy of the hot Big Bang. Fascinating, isn't it?
Absolutely. But what about the regions where the ball stays on the plateau?
Great question. In many regions where the ball stays on the plateau, inflation continues far into the future. However, other regions might undergo this transition sooner. And those weren't necessarily the ones that became our observable universe, but were likely pushed away by the much larger, more voluminous regions where inflation persisted. It's possible that while these other Big Bangs occurred elsewhere in our inflating universe, inflation continued in what became our own universe. This picture, if we choose to visualize it, might resemble an eternally inflating ocean, containing small pockets where inflation spontaneously comes to an end, giving rise to a more slowly expanding region where a Big Bang occurs.
That's an incredible perspective. It's like our universe is just one of many bubbles in a vast cosmic ocean.
Exactly. And on this note, I want to pause and direct my words to our listeners. Isn't it mind-blowing to realize the universe we live in is possibly just one of many? Does it make you feel small, or does it spark a sense of adventure within you? Don't forget to share your thoughts with us. We're exploring deep waters here, folks, and there's so much more to discover. I hope you're enjoying riding these cosmic waves as much as we are. This brings to mind an event from just the other day. I was watching a documentary about space, and it mentioned how the inflating regions between pocket Big Bangs continue to expand more rapidly than any of the regions where Big Bangs occur. In essence, no two pocket Big Bangs ever collide.
Funnily enough, I recently stumbled upon a similar concept while reading a book about quantum physics. It's fascinating how these ideas permeate different areas of science.
Indeed, it's like the universe is constantly expanding and creating new space, much like how each second we live creates a new memory and expands our personal universe of experiences.
It's a beautiful comparison. And just as no two personal experiences ever exactly overlap or intersect, no two Big Bang regions ever collide.
Exactly. And when inflation finally comes to an end where we are, the energy inherent to space transforms into matter, antimatter, and radiation. This event, known as cosmic reheating, marks the transition from an inflationary space-time into the beginning of our hot Big Bang.
In a way, it's like a cosmic rebirth, isn't it?
Absolutely. It's a transition that gives rise to the large-scale structure in our universe today. When inflation ends, that's when the universe we know and recognize truly begins.
Just like our own personal universes, each end is just a new beginning.
Well said. The concept of never-ending inflation reminds me of life itself. There are always new beginnings, new opportunities, and new experiences being created. Just as for every location where inflation ends, there's a new, equal or larger sized location getting created as the inflating regions continue to grow. Wrapping up our journey through space today, it seems that while most regions will see inflation end after just a tiny fraction of a second, there's enough new space being created that inflation should be eternal to the future. Just thinking about that can boggle the mind.
It really puts into perspective how vast and incredible our universe truly is.
It does, doesn't it? Inflation established and created the entire observable universe, gifting the hot Big Bang with the conditions we needed to be consistent with what we observe today.
So essentially, the inflationary universe was dramatically different from the universe we observe today.
Precisely. To comprehend and visualize it, we need to set our intuition aside and embrace a reality where the only energy that matters is the energy intrinsic to the fabric of space itself. This is a profound thought, isn't it? Imagine a reality where the energy within space itself is of paramount importance. It's a brave new perspective for us to consider.
It's clear that our understanding of the universe is continually evolving. As we continue our exploration, invariably, new questions will emerge, and with them, new perspectives and possibilities.
No truer words have been spoken. We've ventured far today, delving into the depths of the universe, its creation, and its endless expansion. But remember, we're just scratching the surface. The universe, in all its complexity and beauty, always has more to reveal. So in a nutshell, we've delved into the concept of cosmic inflation, the relentless expansion of the universe, and the powerful quantum fluctuations imprinted onto the fabric of space. We've looked at how energy transforms during cosmic reheating, initiating the hot Big Bang state, and how this dramatic transition gave rise to the large-scale structure of our universe.
It's like the universe has been constantly setting the stage for its own endless drama.
Beautifully put. And who knows, there might be more acts to come, with inflation likely still occurring in regions of space even today, creating new locations as the inflating regions continue to grow. It's as if the universe is the ultimate magician, forever pulling new rabbits out of its cosmic hat.
That's a fantastic note to end on. We hope you enjoyed this journey with us through the fabric of cosmos, its birth, growth, and the mysteries that it continues to unfold. Remember to blast that like button, leave a comment, and share this episode with your friends. Let's keep exploring the mysteries of the universe together.
That's it from us today. Until next time, keep looking up, and remember, the universe always has something new to reveal.
Bye everyone, and remember, stay curious.
Today's cosmic journey was inspired by the article, "What Was It Like When Cosmic Inflation Occurred?" by Siegel, published on Big Think on November 16, 2023. If you want to delve deeper into this cosmic mystery, you can find the full URL in the description. Until next time, folks.